Hello everyone, Mrs. Belo here. In this video I'm going to be going over some of the example problems in this chapter 12 and 13 recap to review previous material that was covered before spring break, and also to review material that you're going to have to know in the upcoming weeks here. So the first thing I would like to go over is molarity. It won't be coming up necessarily in the upcoming weeks, but it will definitely come up again in the next unit, and so therefore I would still like to review it. So remember, molarity is going to be moles of the solute, whatever it is that you're dissolving, divided by liters of the solution, and most likely your solute will be made using water as a solvent. And if you're looking for molarity, it would be moles divided by liters. And again, you can use this equation here, or you can use the triangle. If you were solving for, let's say, moles, if I'm looking for moles, then that would be molarity times liters. And if I was looking for liters, that would be moles divided by molality. So that is a shortcut to using the triangle. You can also use the equation as well. And just a few more reminders. Remember that 1 liter is equal to 1,000 milliliters. So for example, if I had 50 milliliters and I wanted to get that into liters, I would move the decimal point 1, 2, 3 places to the left. So this would be 0.05 liters. And if I was going from, let's say, 2 liters and I wanted to get that into milliliters, well, you would simply move the decimal 1, 2, 3 places to the right. So that would be 2,000 milliliters. So you can move the decimal, or you can always set up a picket fence, or you can even just do, if you're going from milliliters to liters, you can divide by 1,000. And if you're going from liters to milliliters, you can multiply by 1,000. And then another reminder is if you are working with moles and grams, if you see moles, if you see mass in a problem, make sure that you are calculating molar mass correctly and you're setting up your picket fence correctly. So for example, if I had X number of moles and I wanted to get that into grams, I would have to do 1 mole, and then in the top I would have to do molar mass, which would be in grams. And to find molar mass, you have to use your periodic table. And, most of us know how to do that because we have been doing it for so long. For example, if I had CaCl2, I would do the molar mass of calcium, which is 40.078, plus I have 2 chlorine, and chlorine is 35.45, and I would add those together. I would multiply these first together, and then I would add them together to find my molar mass. If it's something a little bit more complex, something like a polyatomic ion, for example, so let's say I have NaCO3. Let's say I have K. Let me think of an example real quick. So let's say I have MgNO2. So I have 1 magnesium, which would be 24.305, plus, now this is the part that can get tricky sometimes. So this right here is saying that you have 2 NO2s, okay? So that 2 is getting distributed to everything inside of the parentheses. So this means that you have 2 nitrogens, which is 14.007, plus 2 times 2 is 4, and you have 4 oxygens total. So that's a little reminder for how to do those molar mass calculations. So make sure you do the example problem number 1 for molarity. Molality is very similar, except instead of liters, you're going to have kilograms. Now, if we're talking about water, please note that 1 milliliter of water is equal to 1 gram of water because of its density. And also, please remember that 1,000 grams equals 1 kilogram. So if let's say I have 12 kilograms and I need to get this into grams, you would actually move 1, 2, 3 spaces to the right. So this would be 12,000 grams. But let's say I had 6 grams and I wanted to get that into kilograms, I would move 1, 2, 3 places to the right. So 0.006 kilograms. So if you're going from kilograms to grams, you're going to divide by 1,000. And you're going to multiply by 1,000. If you're going from kilograms to grams, you're going to multiply by 1,000. And if you're going from grams to kilograms, you would divide by 1,000. And again, this is just another way to measure our amount of solvent, which typically is going to be water. And then in the top for molality, which is represented with little m. Remember, molarity is represented with a big M. And the top is still going to be your moles of solute. So molality is moles divided by kilograms. If you're looking for moles, that's going to be molality times kilograms. And if you are looking for kilograms, that would be moles divided by molality. My next example problem is on dissociation. This is going to be coming up a lot in this unit. So make sure that you are referring to the back of your periodic table for those polyatomic ions. For example, NO2, this right here, this is a polyatomic ion that is on the back of your periodic table. It is nitrite. So if I'm writing the dissociation of this magnesium nitrite, I would take magnesium NO2, and right now this is something that we would be dissolving into a solution. We would be adding it to water to create a solution. This would almost look like some type of a salt. And once we put it into the water, it's going to be soluble, it's going to dissociate, and we are going to get these two ions being broken up. So you have magnesium, and that is in group 2 on your periodic table. So this is going to be a +2 for its charge. And since it has dissolved, it's an ion, it is now aqueous. Technically, you don't have to write aqueous with this just because it is an ion, and it's by itself, so you can assume that it's aqueous. But I'm going to leave that there for now. And then you have the NO2, the nitrite. Now, this you're not breaking up the nitrogen and the oxygen because this is a polyatomic ion, poly meaning many. This is one individual ion though. And if you look on the back of your periodic table, it has a charge of -1. And this is that ion dissolved in solution. Now you also have to take into account that on the left-hand side here, there was a 2 here. So that 2 now is going to go in front of that ion because this ion, it has broken up into its individual ions. So this NO2 is broken up into each of those individual NO2s or nitrite ions. And again, go ahead and do another example problem here on your own. And I also would like you to count how many total ions you get. Now that's pretty straightforward. All you're going to do is you're going to add these two together, the numbers in the front. So although we don't write it, there's a 1 in front of the magnesium, and we know there's a 2 in front of that nitrite ion. 1 plus 2 would give you 3. Now this is going to be relevant later when we start talking about boiling point and freezing points, and this 3 is going to represent I, which is how many ions you would have, and this is relevant for any type of solution that has electrolytes, which this is an example of an electrolyte because it's an ionic compound and it's something that would dissociate. So again, make sure you're doing all of the highlighted problems on your own. Next, I want to review soluble versus insoluble. So again, you have to use the chart here, and this is going to be coming up a lot in this unit. So what you're going to do is you're going to be looking on the chart here, and you're going to find which of these is in your compound. So as I'm looking at this chart, I can see I have NO3 here, and I have NO3 here. So since it has NO3 present, this is going to be a soluble and therefore aqueous compound. And again, this has no exceptions. If it did have any exceptions that were in that compound, then these would be insoluble. Okay. Let's do another example problem using this chart down here. So I have ZnS, so that's sulfur, which is right here. And I'm going to be looking here at my exceptions. I don't see Zn listed as one of the exceptions, so therefore it's going to be insoluble and it's going to form a solid precipitate. And again, if it does have any exceptions with it, then they would be soluble. So let's do one that has an exception. So I have CO3, and I can see CO3 here, and I notice that the CO3 is with NH4, and NH4 is listed as one of the exceptions. So therefore, this compound would be soluble, and it would be aqueous. Let's do another example problem with one of our exceptions on the top chart here. So we have PbCl2, so here is Cl, and I can see that Pb is listed as one of the exceptions, so therefore this compound would be insoluble and it would form a solid precipitate. And then lastly, we have CaBr2. Here is Br. I don't see calcium listed as one of the exceptions, so therefore this would be soluble and therefore aqueous. One important thing to remember is on this chart here, you have the alkali metal cations listed as exceptions. So remember that these are group 1 metals. So this is going to include your group 1 alkali metals, so lithium, sodium, potassium, rubidium, cesium, and francium. It was a lot easier than writing them all out in this chart. It was just easier to tell you what group they were in. And go ahead and again do those example problems on your own. And then in another video, I'm going to go over something we haven't covered since last semester, which was double replacement or displacement reactions, which we're going to be seeing in the upcoming weeks here, and I'm going to make a separate video for that.